on? Yeah, it's on. Okay. So I was just discussing this local well-posedness proof. And one thing it does for us, we don't, for the remainder of the course, we won't mention the details of local well-posedness directly, but it actually gives us a definition of what we mean by blow-up. So in that sense, it's very important. And this proof can be modified to give us a lower bound on the blow-up, what's called a lower bound on the blow-up rate. So I will discuss that. Let me go, let me just start over here. So this local well-posedness proof requires that the time be chosen small depending upon the size of the initial condition in H1. So it's 1 over that norm to some power, and if you follow the details of that proof. So then we can just say, we'll pass to the maximum such time on which we have existence and uniqueness in the sense that I described. So let t star, as soon as you know that there exists a t positive, you can just say take the sup, and I know it will be positive. T star equal to the maximal time of well-posedness. All right, so that would mean then that we would have U would be continuous as a map from 0 to, let's say, t prime into hx1 intersect w l t prime q w x1r for all t prime strictly less than t star, this maximal time. But if t star is indeed the maximal time, and if that maximal time is finite, then there must be some breakdown at t star. So if t star is finite, then we must have that the limit as t to t star of the gradient u of t Lx2 is equal to infinity. And the reason that this must happen is that if there was a sequence of times, Tn approaching t star on which this was bounded, then I could use the local well-posedness proof that we just discussed and obtain a time t that depends upon that bound such that I could advance from each point by that amount. So let me just write it. So suppose that there exists Tn up t star such that, this is a proof, such that the gradient is bounded by some r along that sequence. Then by the well-posedness proof, there exists some t which depends upon r such that we get existence and uniqueness, well-posedness, on Tn to Tn plus t. And then as Tn approaches T star, eventually Tn plus T will exceed T star, and you'll get a contradiction to being maximal. But that, of course, assumes that T star is finite. If T star is equal to infinity, then I can't say anything. You can have that the gradient of u goes to infinity or remains bounded. Both are possible. Okay, so this is then our definition of blow up in finite time. So in this case, we say u of t blows up at t star, at t equals t star. In the physics literature, it's sometimes called collapse. We always call it blow up. The well-posedness proof gives you extra information in this situation. We have the following. This would be proposition on the lower bound of the blow-up rate. So it says that there exists a constant such that following holds. So it's a universal constant C such that if u of t blows up at t equals t star, and that's finite, then this quantity, the L2 norm of the gradient of u of t, must not only go to infinity, but it must go to infinity at a certain rate. And that's t star minus t. 1 minus sigma sub c over 2. So sigma being the critical Sobolev index. This is for little t sufficiently close to capital to t star. Okay. And this, so this follows from the estimates the well-posedness proof. It is also connected with the scaling of the equation. I'm going to skip the argument so I have enough time to talk in detail about ground states. So for example, if we're dealing with the L2 critical case, so this is L2 critical, and there you have nonlinearity P equals 1 plus 4 over D. So think D equals 2 and P equals 3. Then this just says that this quantity must diverge at the square root, at least at the square root rate as we approach the blow-up time. It turns out that we never see this rate. The slowest rate we actually see is this with a log-log correction. And the explicit blow-up solution that we can write down using the pseudo-conformal transform of the ground state blows up much faster at the rate 1 over t star minus t to the 1. Okay. All right, so let me discuss ground states in more detail. Ground states so we want the solution. We're talking, when we mention ground states, we mean a solution to this equation, which, as I mentioned before, think of it as a nonlinear eigenvalue problem. We want a non-zero solution of minimal mass. So mass is LT norm squared.
Justin,
Yeah.
when this proposition, the first one,
Yeah.
you prove that you have the limit. This is for the subcritical case, right?
Yes. Yeah. So this is for energy subcritical. So I restricted to that case.
The second one that the property that you brought up.
Yeah. Right.
The second one is also
Yes. I only discussed well-posedness in this case. That's because in the critical case it's.
the example one applies to the
No, there's the L2 critical. L2 critical, which is P equals 1 plus 4 over D. That's, this is energy critical, or H1 critical, which is much bigger, way out of bounds of what we would deal with here. Yeah, actually, so the energy critical case, of which a typical example is D equals 3, dimension 3, and P equals 5. Or D equals 4 and P equals 3. That's been studied quite a bit over the last decade, what is meant by the notion of local well-posedness is more subtle in that case because the time interval, the length of the time of existence and uniqueness depends upon not just the H1 norm, but also the more detailed structure of the initial condition. And so passing to the global well-posedness is a much harder problem, and understanding blow-up is also subtle. Right, I was going to state this a little bit later, but another thing to mention here is if it's something that tells you that you have a bound on the gradient of U in L2, like energy conservation, then you know that the solution has to be global. So blow-up can only happen, in this situation, an a priori bound, as we call it, of the form this would imply that you know that this quantity has to remain bounded because of energy conservation is usually the mechanism by which you draw that conclusion, then U is global. But I thought I'd discuss that after we discuss ground states. So our interest in this is that, well, first of all, it gives us the solitary wave. So it's U of xt equals e to the it q of x. This is the solitons or solitary waves. And it's just simple to check that this will solve NLS if Q solves this equation. And then you can apply Galilean invariance and scaling, get traveling waves. You can also apply the pseudo-conformal transform to this and get an explicit blow-up solution. I will write that down in a little while. And it turns out that if you study solutions to the L2 critical equation that blow up and have mass close to the mass of Q, then they have to be, as we go into the blow-up, they have to be well modeled by Q. That is, Q is sort of a blow-up profile. The blow-up will be described by a rescaling and phase shift of Q. The reason we know that is because Q has very strong structural properties and has a variational characterization. Okay, so we can carry out the proof of existence and uniqueness for ground state solutions Q to this equation if you work in, you can work in Schwartz class if P is equal to 3 or 5, because then you have Q squared Q or Q to the 4 Q, so it's an algebraic power, and you don't run into problems when you take derivatives. Otherwise, you can do everything in a function class, I don't know what to call it, V of Rd, which would be equal to the set of all U, which are C2, and such that there exists constants for which we have all second-order derivatives decay exponentially so you have two derivatives, and those, the function itself and the first few derivatives decay exponentially. So this is, so we can prove existence and a certain type of uniqueness. Because there's invariances that actually kill uniqueness, but once you clear out invariances, then there's a uniqueness statement of ground states. Q belonging to this function class V. And so the first thing that that you should do before trying to prove existence is say if you have a solution Q and it has this nice regularity, then what kind of properties would it satisfy? And the Pohojayev identities are what you get. So these are any solution, in fact. So any Q, not just ground state. I mean, ground state refers to minimal mass, so it's a special type. But any Q in V solving this equation so I mean, you do need some integrability because Q equals 1 solves that equation, and then the identities would be meaningless. But and this is for P in this energy subcritical range. So this is then there is a relationship between the L2 norm, the LP plus 1 norm, and the L2 norm of the gradient. Sigma 1 to define this. LP plus 1 to the P plus 1, sigma 1, L2 So it suffices to write those two, but you can use those two to give you this relationship as well. Sigma 1 is just convenient to use notation for this quantity. That is, if I write it as follows, sorry, 1. You will recognize that as the number of derivatives that show up in the Sobolev embedding estimate. Sobolev embedding, which is U in LP plus 1, bounded by constant times d sigma 1 U in L2, also written as U in H sigma 1 dot. Right, that's just the Sobolev embedding relationship. So it turns out that whenever the critical Sobolev exponent is less than 1, then necessarily sigma 1 is also less than 1 and it's bigger than sigma sub c. For example, in d equals 2 and p equals 3, and sigma sub c is equal to 0, it's an L2 critical case, then you have sigma 1. So say d equals 2, p equals 3. We have sigma 1 equals it's a 2, yeah, it's a 1, so it's a 2, yeah, it's a half, right? Yeah, it's a half. So what this enables you to do, so you have 4 quantities here, L2 norm, LP plus 1 norm, and L2 norm of the gradient. And if you know any one of them, you can solve for any of the others. But in dimensions 2 and higher, you don't know any one of them unless you do some numerics to find out. So you can numerically compute the ground state and find its mass, for example. But actually, so this is not just about ground states. It's about any solution to this equation with this regularity property. So it shows you that the statement minimal mass can be characterized in a number of other equivalent ways. You could say minimal H1 dot norm if you want, for example. Or what's more important for us is that we could say that Q is a ground state if and only if it is a minimizer of this action given by I of u equals u L2 to the p plus 1 times 1 minus sigma 1 gradient of u L2 p plus 1 sigma 1 over u in L p plus 1 to the p plus 1. Okay. Where does that come from? That comes from, if we look back at this Sobolev embedding, we can deduce the so-called, sometimes called Gagliardo-Nuremberg inequality as a consequence. So the right-hand side here is also c to the sigma 1 u in L2. Hat. Definition, right? So then you use Holder's inequality, then just tells you, it's weight interpolation, it's just Holder's inequality, that L2 to the sigma 1 gradient of u in 1 minus sigma 1 to the sigma 1 Well, because first you do Holder's inequality, so it's still on the Fourier side. You still have that, but then you use Plancherel's theorem, and you get back to this. So you have that. So there's a constant here. It's just a constant from Sobolev, starting from the constant from Sobolev embedding. You end up with a constant here. And if you raise this inequality to the power p plus 1, and then divide by the left-hand side, then you get this. So what this inequality says is that I of u is bounded below by some positive number. So this is this version is sometimes called Gagliardo-Nuremberg. So we'll just say Gn. So Gn then says that that I of u is there exists m tilde positive such that m tilde is less than I of u for all u in H1. So it's just dividing by this and raising to the power p plus 1. And so this is then a variational problem. If we can construct a minimizer of this, then we can prove the existence of ground state and at the same time show that it saturates this inequality. So then the goal for constructing minimizer, constructing ground state is to prove existence of minimizer of I. So this is a variational problem. You can check that the Euler-Lagrange equation for I is not exactly the equation that I wrote down for Q, but it's after rescaling it becomes the equation for Q. So you construct a minimizer, you then rescale it, and then you get a solution to that Q equation. And it will be it will then have to have minimal mass because of these Pohojayev identities. The Pohojayev identities enable you to re-express this quantity so that it's just given entirely in terms of the L2 norm. For a minimizer, i.e., for a minimizer for a solution to that equation. Yes. Yes.
You talked about the rho infinite time.
Yes.
And then you change to this ground state.
Yes.
Looks like permanent regime. I mean, this is relation.
Right. Well, okay. So this has a variational characterization. And then that variational characterization says that if we're studying a solution that blows up for the L2 critical equation, it has to be modeled by this Q. Okay, so let me. All right, so there's a lot to say about the calculus of variations problem involved here. But let me just state this variational characterization. So this is a variational characterization of Q. Okay, for each epsilon, there exists a delta such that the L2 norm is close to the L2 norm of Q. So these are all assumptions. The gradient in L2 is close to the gradient of Q. And LP norms are close too. Seems like a lot to ask, but there's Powajoyev identities and other tricks. Then V has to actually be close to Q, but the invariances force us to put phase e to the I theta, a Q, and allow for a shift. So that's H1 less than epsilon. So that there exists some phase and some spatial shift such that V is actually in H1 close. So you just start with statements about the size of various norms, and you get a statement that V is actually in a function space sense close to Q. And that actually comes out of this variational analysis. So let's look at this L2 critical case and derive a different form of this. Okay, so in the theorem, this is really a corollary of this. Take P equals 1 plus 4 over D. And for each epsilon, there exists a delta such that if the L2 norm is close to the L2 norm of Q, and the energy is less than delta times rho to the minus 2. Where rho is defined to be gradient of Q over the gradient of V. Then, so it's these two assumptions then give us we have that rho to the d over 2 V rho x minus e to the I theta 0 q of x plus x0 in H1 is less than epsilon. So in this case, we can say that if the L2 norm is close to that of Q, and remember for Schrodinger evolution, the L2 norm is conserved, and the energy satisfies this bound, then a rescaled version of V has to be close to Q up to invariances. And so if you have, I'll prove that as a consequence of this seemingly stronger statement, but to apply it, just take a solution that is blowing up. So suppose U of t solves L2 critical, so we call it just critical NLS. And it's has L2 norm, bigger than Q, but not too much bigger. So I'll mention in a moment how if actually the L2 norm is strictly less, then you get, then it doesn't blow up. Right, so the L2 norm is close to the L2 norm of Q, and it blows up. At some t star. Then the conclusion has to apply, right? Because U of t will satisfy this. And then the energy is also conserved. But on the right-hand side, you have rho, and there is the gradient of u of t, which we're assuming we blow up. So therefore, the gradient of u of t goes to infinity as we approach the blow-up time. So rho goes to 0, but then it's rho to the minus 2, which goes to infinity. So you have a fixed quantity. And on the right-hand side, as t approaches t star, it's diverging. So eventually, this will become true. So that's true, this is true, and therefore, that holds. So then, for each t close to t star, you can invoke this. So there exists theta of t and x of t such that rho of t to the d over 2, u of rho of t x comma t minus e to the I theta of t q of x plus x of t h1 plus an epsilon. So what that is saying is that the solution is well modeled by Q as it blows up. Now the rho of t is just defined to be a gradient of Q over the diverging quantity gradient of u of t in L2, and that is going to 0, to 0 as t approaches t star. So it's contracting to a point because of the rescaling. So therefore, in the study, if you want to construct a blow-up solution, you would start with Q and look at the behavior of solutions in a vicinity of Q. That is, you consider the linearization of the NLS in a around Q, and look at its spectral properties, and that's the sort of things that we'll do in the next lecture. So we say that Q is a blow-up profile. So that's one conclusion you get out of this. Another conclusion is that Q saturates this Gagliardo-Nuremberg inequality. So we go back and look at the energy. So again, to take the critical case, 1 plus 4 over d, and look at the inequality C. There's a constant that depends upon P and D here. And then there's 1 minus sigma 1 and gradient of U L2 and sigma 1. And the constant is achieved when you take u equals q. That's because the equivalent construction was just by minimizing the corresponding functional. So this becomes q in LP plus 1 over q L2 gradient q L2 sigma 1. So you can take this quantity, this as the constant here, and of course it's the best constant that you can use because you take u equals q and you get the same thing on both sides. So then you go and look at the energy. The energy of u is conserved, and it's given by 1/2 gradient of u of t in L2 squared minus 1 over p plus 1 u of t L p plus 1 to the p plus 1. So this is the quantity on the left-hand side of that inequality. But we have a minus. So we get that this is bounded below by 1/2 L2 squared minus, you have to put that constant there. But then you can put u of t L2 to the 1 minus sigma 1. That's p plus 1. That's the gradient of u t L2 to the sigma 1 times p plus 1. And in this case, the critical case, so for p equals 1 plus 4 over d, I claim that that number, sigma 1 times p plus 1, is equal to 2. So that's 2. And this is also a 2 power. So then this is the L2 norm, which is conserved. So you have some constant here. And so the question is, what is 1/2 minus this? And if you use this expression for this constant, the sharp constant, together with the Pohojayev identities, which enable you to convert between any one of these quantities, you can re-express this in terms of the mass alone, then this can be shown to be a half with q L2 1 minus sigma 1 p plus 1. Okay, so that's by Pohojayev. So even though we don't know what the mass of q is, we still can get that. So therefore, you have, we can write it as 1/2 times 1 minus u over q to this power, which I guess it's, I guess it works out to be p minus 1. P minus 1. Yeah, it has to work out to be p minus 1 in this case. Times the gradient of u of t. All right, so the L2 norm is conserved. So this is just a fixed number. So if you start with initial data for which the L2 norm is strictly less than the L2 norm of q, then this number is positive. And the inequality furnishes an upper bound on the gradient of u of t in L2. So conclusion. if U0 L2 is strictly less than Q L2, then the gradient of U of t is bounded by some constant depending on the energy. Energy is conserved. And so U of t is global. It does not blow up in finite time. On the other hand, another thing we can say is that if the energy is negative, then we do have to blow up in finite time. So if so this is different. So on the other hand, if the energy is negative, then U blows up in finite time. Does blow up in finite time. So this is, strictly speaking, this is only known if you work in the space, which is often denoted sigma, which is H1 plus X U in L2. So you need finite variance. And it's a consequence of the so-called virial identity, which is another identity. And let me state the version for general P in the case of the L2 critical. In the L2 critical case, well, all right, so in the L2 critical case, we'll just say that it's 16 times the energy. This is in the P equals 1 plus 4 over D. It's a little more complicated for other P's. But in this case, it's just proportional to the energy. And so if this energy is negative, that's what I'm assuming, then the convexity of this function is negative. So it's concave. It's if we graph this function of time, if we graph it, it has to be a parabola with a negative quadratic coefficient. So even if initially it's very high and the initial slope is very high, it's eventually going to come down and hit 0 in finite time. When it does hit 0, so let's say we calculate that it hits 0 at t star star. Well, that is a time at which x u of t star star is equal to 0. And so therefore u at that time is equal to 0, which is a contradiction. So therefore blow up must have occurred at some previous time. Or at, I guess it could occur exactly at that time as well. So blow up has to occur at some t star less than or equal to t star star. So that this was observed by Glassy in 77, but there's also some Russian papers a few years before that. At any rate, I was giving a talk, and Rodniansky told me it was in Landau and Lifshitz. I didn't check. So that's a different, that's a different argument in which you're appealing to an identity. But when can the energy be negative? Well, I mean, it's a consequence of these two observations that we can only have negative energy when the mass is strictly, so you can only have negative energy when the mass is bigger than the mass of Q. However, there are U's for which the mass is bigger than the Q mass, and the energy is positive, and then in that case, you don't know what happens. You can have blow up, you might not have blow up. So this picture is not complete. It says that if you have the mass less than Q, then you're global. If the mass is bigger than Q, I don't know. But if the energy is also negative, then you do blow up. Okay. Where are we on the clock? Oh, just about at the end. That's a shame. So there's a few more things that come out of this variational analysis of Q. And one of them is that if you have a solution to the critical NLS that blows up, then it has to concentrate at least the ground state mass. That the mass, as we approach the blow up, there has to be a point into which at least a ground state amount of mass concentrates. And then another thing is a complete characterization, and this was obtained by Merle in 93. So Merle in 93, but then simplified considerably by Hamidi and Karani in 05, is that if U, 0, or U of t in L2 is equal to Q, and U blows up, then it must be then U0 must be very specific. It must be given by Q with a quadratic phase. So you have just a standard constant phase, but then an e to the minus I x squared over 4t star. So this is what it is initially. So there's just rescalings and shifts that we have to allow for, but there's a negative quadratic phase, and so this must be a pseudo-conformal transform of this, so i.e. U of t, the solution, is a PC transform of e to the it q of x with, with invariances, so phase and shift and so forth, phase, shift, scale. So that's you take e to the it q of x and apply the pseudo-conformal transform, and you get the special formula, which I guess I never did write down. Maybe I should just write it down. You take u xt equals e to the it q of x. Then we apply pseudo-conformal transform as I wrote it. And we get, so we apply PC, and we get, so look at U1, and then we get the U2, and that is e to the I x squared over 4t over 2, t to the d over 2, q of x over 2t e to the minus I over 4t. Then you can rescale and translate in time. And you get what people usually write as sxt, which is e to the I x squared over 4t over t to the d over 2 q x over t e to the minus I over t. I guess that's just rescaling. And then, but then you can translate in time. So you have s of x t minus t star is a solution that blows up at t star. For, you know, choose any t star you like. You get a solution that blows up at t star, and you see that it then becomes e to the minus I x squared over 4 t star minus t. And then evaluate that at t equal to 0, and you get this. So it's this solution evaluated at little t equal to 0, which is essentially this, except for the scalings and the shift. Right. So you know you have these solutions, but then this is a very strong rigidity statement, which says that any solution with mass exactly equal to q that blows up has to be that solution. Okay, so that's all for today. All right. Thanks, and hopefully see you tomorrow.